So next, chapter 5, coordination compounds. So in this chapter, what are the key points you have to thorough? First, introduction. In introduction part, you must be thorough with double salt with example. And you should know the difference between the double salt and the coordination complex, right? In introduction part, you must learn two questions. One is, what are called double salt? Give examples. Is it clear? Example, more salt, potash alum, those things you can write. And the difference. In double salt, the constituent atoms or ions will not lose its individual property. But in elements get into complex, it losing its individual property. And in this chapter, you have three theories. Definitely you can expect one question from the theory part. Werner theory, valence bond theory, and Kesselfield theory. See, whenever you are studying the theories, you must learn the limitations also, which means drawback. So, theories means postulates and limitations. Both you must learn. And VBT, some applications also there that I will show in the next slide. So, Werner theory, what is the example we have taken? CO, NH3 6 times Cl3. So, by using this example, you must explain primary valency and secondary valency. Write the postulates of Werner's theory. It's a straight question. Differentiate primary valency and secondary valency. So, in which a point is primary valency and secondary valency. So, what are called primary valency? What are called secondary valency? Primary valencies are ionizable, responsible for the oxidation state of the central atom or oxidation number of central atom. They do not have directional property. In case of secondary valency, and one more thing, primary valency always satisfied by negative ions. In case of secondary valency, satisfied by negative ion or neutral molecules, which are called as ligands, and they are directional in nature, responsible for coordination number. So these points you have to highlight for the difference between primary valency and secondary valency. And valence bond theory. In valence bond theory, see, while writing the postulates, you must mention intermixing of the metal orbitals and ligand orbitals. That is called hybridization, right? If you don't know the proper statement, at least write intermixing of metal orbitals, metal d orbitals and ligand orbitals. So the process of intermixing of orbitals are called hybridization. And also you should draw a table for correlating that. Here hybridization and what will be the geometry, right? At least coordination number, and the coordination number also you can write it here. So coordination number 4 and 6 you can take that. Coordination number 4, you have two types of hybridization, sp3, dsp2, and 6 also you have sp3 d2, d2 sp3. So for coordination number 6, geometry is octahedral, here sp3 tetrahedral and dsp2 square planar. So don't forget to draw this table. And one more point also you can mention that sp3 and sp3d2 are called as outer orbital complex. When the hybridization starts with the d orbital, that will be called as inner orbital complex. So these points you must remember for valence bond theory. And crystal field theory, it considering point charges, that ligands were considered as point charges, and when ligands approaching the central atom, the energy of the metal d orbital split into two different levels. One is lower energy, another one is higher energy. So how far a splitting take place in octahedral complex and tetrahedral complex? The two diagram also you must draw that, because maximum they are asking draw the crystal field splitting for tetrahedral complex or octahedral complex. So the diagram you must draw. For octahedral, T2G down and EG at the top. For tetrahedral, E and at the top T, T2. So no G, right? So keep that in your mind. And next, isomerism, geometrical isomerism, structural isomerism. So here, cis-trans isomerism, you may be asked to draw, or maximum MCQ only they are asking. They will give one complex, find out what type of isomerism possible. So cis-trans or facial or meridional or optical isomerism or these four, right? So cis-trans means when ligands placed or lies at the same side is called cis. Opposite side means trans. Cis and trans also only applicable for square planar and octahedral. It is not applicable for tetrahedral. The reason is the relative position of the ligands with the central atom are not equal, which means all the four bonds are not equal. Simply you can write it, right? And facial and meridional. Actually, when the ligands are placed at the corner of the face, then actually you can take CO, right? Cl, 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 NH3, NH3, NH3. So this is, see, on the face, similar ligands lying. It's called facial isomers. Instead of that, meridional point, right? Actually, this is called at the corner. When the ligands placed at the corner of the face, called facial isomer. When the ligands are placed meridional point means like this trigonal, right? Actually, Cl, Cl, instead of this NH3, Cl here. So remaining these three, NH3. If you draw like this, that's called meridional isomers. The same example you can use it for representing facial and meridional. And optical isomers also called as mirror image isomers, which have non-superimposability, chirality. And structural isomerism, coordination isomerism, when two complexes exchanging the metal alone, this metal 1, metal 2, and this will be forming isomer with metal 2 and the other complex with metal 1. So this and this are what? Coordination isomers. Here whatever the ligands will make you, right? And hydrate isomerism or solvate isomerism, both are same only. Based on the number of water molecule present in the coordination sphere. How many water molecule present in the coordination sphere? That's called hydrate isomerism or solvate isomerism. And ionization isomerism. What kind of ions formed? If you take CO, NH3, Br, SO4. When you ionize, this will give simple anion, sulfate, SO4 2 minus. When you bring this sulfate to the complex, and then it will give CO, NH3 5 times, SO4 and Br. Now it will form Br minus as anion. These two are ionization isomers. And linkage isomers formed by the ambidentate ligand Cn minus, NO2 minus, SCN minus, right? Actually NO3 minus, it is not ambidentate. NO2 only, right? Because the MCQ, which of the following act as ambidentate ligand? In options, NO3 minus and NO2 both will be given. NO2 minus only the right answer, right? So linkage. So what? Which atom is linked? Here carbon also may be bonded with the metal atom and also nitrogen, right? Ambidentate ligand means is a monodentate ligand which have more than one donor site. Here carbon also can donate nitrogen also can do. Here NO2, nitrogen also can donate electrons, oxygen also can do. So such a way we can give the explanations. And next, what are the terms we are using in coordination? Actually, see, coordination, this is the first one, second one, third one. Coordination entity, which means a complex which have metal and ligand. That's all. A complex which have metal bonded with ligand is called as coordination entity. What is coordination sphere? When a complex represented in square bracket. When a complex represented in square bracket is called coordination sphere. Right? And where the arrangements, lattice arrangements in three-dimensional space where the metal atom and ligands are arranged. The arrangement of central atom ligand in the three-dimensional space is called coordination polyhedron. So this one is arrangement of the same word only we are using. Arrangement of the central atom and ligands. See, coordination entity, coordination sphere, coordination polyhedron. The similar terms only we are using. And central atom. The metal atom exists in the coordination sphere. So this is coordination sphere, right? Square bracket, in which the metal present is called central atom. And coordination number, the number of bonds formed with ligands by the central atom, that may be 4 or 5 or whatever may be the count, formed by the ligands with central atom, called coordination number. And oxidation state of central atom or oxidation number of central atom, which is nothing but the charge carried by the central atom in the coordination complex. The charge carried by the central atom in a coordination sphere or polyhedra, whatever, which is called oxidation state or oxidation number of the central atom. And next one is homoleptic heteroleptic complex. See, so metal bonded with similar kind of ligands. This is called homoleptic complex. When the metal bonded with different kind of ligands, NH3,5Br. Now two different ligands, right? When more than one kind of ligand present in the coordination sphere is called heteroleptic. Only one kind of ligand present in the coordination sphere is called homoleptic. That example also you can take. Negative ligands. Actually, ligands, what are called ligands? Ligands are electron donor to central atom in a coordination sphere, right? Simply you can define what are called ligands means ligands are electron donor which donate electrons to central atom in a coordination complex. Then what is the role of ligands? Electron donor. So electron donors also called as Lewis base. Then what about central atom which accept electrons? Lewis acid. That's the MCQ question, right? When ligands carries negative charge, called negative ligands, are capable of donating electrons to central atom. And neutral ligands. Ligands do not carry any charge but capable of donating electron to central atom. Ambidentate ligands. Ambidentate ligands are monodentate ligands which can coordinate with central atom more than one way or which have more than one donor atom. And chelating ligands. Chelating ligands are the ligands which make more than one bond, which can coordinate more than one bond and forming a ring structure. That is important. Forms ring structure. Forms 5 or 6 membered ring structure. Capable of forming more than one bond with central atom. Capable of forming more than one bond with central atom. and form 5 or 6 membered ring structure. Monodentate, ligands which can donate only one pair of electrons to the central atom. Bidentate, ligands which can donate 2 pair of electrons to the central atom. And example, Cn minus, Br minus, Cl minus, NO2 minus, NO3 minus, right? For bidentate, En, C2O4 2 minus, ethylene diamine and oxalato ions. These two are the example for bidentate. See En, when you consider this one metal which can make 2 bonds, bidentate, right? And the next one, applications of valence bond theory. Valence bond theory mainly used to find out the hybridization. With the hybridization, we can predict the geometry, right? So what are the hybridization they list out here? sp3. sp3 means tetrahedral. dsp2 square planar. sp3 d2 and d2 sp3 are octahedral. And here magnetic moment also you should calculate. So magnetic moment formula, mu s is equal to square root of n into n plus 2 bm. Bm is a unit, Bohr magneton, right? Depends on the number of unpaired electrons. Depends upon the number of unpaired electrons, that mu s value will changes, right? So 1.7, 2.8, 3.8, 4.9, 5.9 different values, right? And while starting the revision, I mentioned that difficult level 23 marks, right? Here also a question is that calculate the number of unpaired electrons. Calculate the number of unpaired electrons if mu s value is 4.9. It's a numerical only, right? Actually, what is the meaning for that? 4.9 is equal to square root of n into n plus 2 bm. Am I right? So when you remove the square, you should take square for here. Sorry, you should square it, right? Not square root. So 4.9 square, which is equal to n into n plus 2 bm. Then n square plus 2n, n square plus 2n bm, right? Which is equal to 4.9. You can expand that, n square plus 2n minus 4.9 square. Am I right? It's a quadratic equation. Sir, we are very weak in maths. No issues. No issues. The very next step, you can write the n value. Mu s value 4.9 means how many number of unpaired electrons? That's all. Directly you can write. That's all. You must write the steps. You need not to chart out the equations and find the values and all, right? Write the quadratic equation, then write the answer. N is equal to 4. Suppose mu s value 5.9 given means n value 5. But the steps which are very important. Is it clear? Sir, mu s value given directly, I know the answer. No. Step mark will be there. You have to write all the steps. Is it clear? For removing square root, you should square both sides. Then only the square root will be cancelled. And metal carbonyls. So metal carbonyls also very important. Just to go through the synergic bonding. Synergic bonding. Actually, ligands only donate electrons to metal. When metal donate electrons to ligand, here ligand is carbonyl. That back bonding only called as synergic bonding. That back bond only called as synergic bonding. And at the last end of the chapter, applications of coordination compounds. There are 3 applications we have: analytical use, biological use, medicinal use. Definitely you can expect 1-2 more questions from these applications. So don't forget analytical use, extraction process, then isolation process. Isolation of metals and extraction of metals. And in dyes also we are using biological process, hemoglobin and chlorophyll. Hemoglobin Fe exists in 2 plus oxidation state, and chlorophyll magnesium exists in 2 plus oxidation state. Both have octahedral geometry. And medicinal uses, cisplatin, anti-tumor drug, treatment for cancer, and EDTA, so food poisoning medicine. Apart from that, silver bromide also we are using in photography. Is it clear? So that's all about the coordination number. So just thorough all these contents, definitely you will get 7 marks from this chapter.